Welcome to this webinar on methods for the detection of soluble salts. My name is Bill Corbett with KTA-Tator Incorporated in Pittsburgh, PA, and I'll be hosting this webinar today. During this webinar, I'll be describing the purpose of SSPC's Guide 15 on the retrieval and analysis of soluble salts. And I'll be showing you a list of ISO standards for extraction and analysis of soluble salts. And I'll be describing various methods of surface extraction and analysis that can be done in the laboratory, shop, or in the field. I'm also going to be describing a procedure for converting conductivity measurements to surface concentrations. What we're not going to be discussing in this webinar are the precise step-by-step instructions for the various methods of extraction and analysis. In fact, hands-on training with the various kits is probably the most effective way to become more comfortable with the procedures. Also, there is a boiling method that is described in Guide 15, and since that's primarily a laboratory procedure, I'll not be describing that either. Finally, we'll not be addressing the selection of sampling locations in the field or shop, the number of samples to collect, or any acceptable levels of soluble salt contamination. There's 7 learning outcomes or objectives for this webinar. So when we're done, hopefully you'll be able to describe the purpose of SSPC's Guide 15, be able to list 6 parts to the ISO standards that all address soluble salt extraction and or analysis procedures, be able to describe the difference between sample extraction and analysis of the extracted sample. Describe 6 different methods available for extracting a sample and 7 different methods for analyzing the sample. Be able to calculate surface concentrations based on the concentration of soluble salt in the collected sample, the sample volume, and the size of area where the extraction occurred. And finally, be able to convert conductivity to surface concentration. SSPC published a document called Guide 15, which is titled Field Methods for Retrieval and Analysis of Soluble Salts on Steel and Other Non-Porous Surfaces. This document describes common field methods for extraction and analyzing soluble salts. The intent of the guide is to assist the user in selecting a method or procedure for retrieving samples from the surface and then analyzing those samples for chloride or conductivity. The advantages and limitations of the various methods are described to help the user decide which method or methods will work best for their application. The guide does not contain any information regarding acceptable levels of surface contamination. These levels are best established by the specifier. In addition to SSPC's Guide 15, ISO has published a standard for the preparation of steel substrates before application of paints and related products, specifically tests for the assessment of surface cleanliness. The particular ISO standard 8502 contains 6 parts that all address chloride detection and analysis. Part 2 describes a laboratory procedure for determining chloride concentrations on clean surfaces. In summary, this method involves washing a defined area with a known volume of water, then performing a manual titration. It's not practical for shop or field use, so we'll not be describing it in this webinar. Part 5 describes a procedure using ion detection tubes to determine concentrations of chloride contamination. We will be describing this method in the webinar. Part 6 of the ISO 8502 standard describes an extraction procedure using latex patch or cell method, which we'll describe. Part 9 of the standard describes the use of conductivity meters for detecting ionic contamination levels in test solutions. And Part 10 describes a titration procedure that is used to determine chloride concentrations in a collected solution. Known as drop titration, this method can be performed in the laboratory, shop, or in the field. Finally, Part 12 of the ISO standard describes a titrometric procedure for detecting ferrous ions rather than chloride. Copies of all of these standards and their parts can be obtained through the American National Standards Institute, or ANSI. There are two basic steps to determine how much soluble salt is on a surface. These two steps are extraction and analysis. While there is instrumentation that can perform both of these procedures almost simultaneously, the contamination must be extracted from the surface before it can be analyzed. Surface extraction is the sampling of a known sized area for the purpose of assessing the level of contamination. There are several methods we can use to perform a surface extraction. Analysis is the actual testing of the extracted sample for specific anions or for conductivity. There are several extraction and analysis methods for determining whether chloride or other anions are present. To select a test method, first ask yourself, what does my project specification require? If the specification does not require a specific method, then you can select from any of the methods that are described in this webinar. I'll be describing 6 methods of extraction, including swabbing, latex sleeves and cells, saturation of a contact pad, magnetic cells, and filter paper saturation. With the exception of swabbing, each of these extraction procedures has a proprietary name and even a proprietary instruments that are used in some cases. Some proprietary information and digital images are included in this webinar. This is not meant to be an endorsement of these products, but simply an illustration of their existence. Also, there may be other methods of extraction that I'm not going to be addressing, and no doubt there will be better mousetraps in the future. This webinar will address the primary methods of extraction that exist in the marketplace today. I'll also be describing 7 methods of analysis, including chloride ion test strips and detection tubes, drop titration, ferrous ion and nitrate ion test strips, a colorimeter for determining surface concentrations of sulfates, and conductivity meters. Each of these analyses also has a proprietary name and even some proprietary instrumentation associated with it. Similar to extraction, there is some proprietary information and digital images included in this webinar as a convenient way to describe their use. These should not be considered product endorsements. Further, there may be other methods now or in the future that can be used for analysis of an extracted sample. This particular slide illustrates compatibility between methods of extraction and analysis. While there are prepackaged kits available, the user does have some flexibility if they prefer a certain extraction and analysis method that is not prepackaged. For example, if surface swabbing is the method used to extract a sample from the surface, denoted as E1 in the chart, the extract can be analyzed using chloride ion test strips or detection tubes, drop titration, or even using a probe type conductivity meter. These are denoted as A1 through A4 in the chart. This is also true of latex patches or cells. If the latex sleeve is used, which is denoted as E3 in the chart, then the same methods of analysis can be used with the exception of the conductivity meter, since it is not compatible with the proprietary extraction liquid used in conjunction with the latex sleeves. Each of these methods of extraction and analysis will make a lot more sense as we move further into this webinar. The first extraction procedure that I'm going to be describing is the swabbing method. It's not the best, but it was probably the first method ever marketed for the extraction of soluble salt contamination on surfaces. Some work done by SSPC indicated that it actually produces a very low extraction efficiency, arguably the worst of all the methods described today. However, it was the first It was the easiest to approve upon, and certainly industry has done that. The prepackaged kit contains all of the necessary equipment needed to collect a sample from the surface, then test the sample for chloride, ferrous ion, and pH. There are a few calculations that have to be performed once the extraction is complete. First, select a test area based on the project specification requirements or other instructions. Once a test area is selected, measure and draw a square on the surface using a non-chloride permanent marker. The square can be any size as long as you measure and record its dimensions. A 15 by 15 centimeter sample area is convenient because it converts to 225 square centimeters. Dispense the desired quantity of distilled water into the plastic graduated cylinder supplied with the kit. You can use any amount of water, but the more you use, the more likely it will dilute your sample. Therefore, for a 15 by 15 centimeter area, 22.5 milliliters of solution is recommended. For smaller areas, use less water. Record the amount of water that you actually used. Pour all of the water from the graduated cylinder into a small plastic beaker supplied with the kit. Using the tweezers supplied with the kit or using non-chloride latex surgical gloves, remove a cotton ball from the Ziploc bag. Immerse the cotton ball in the sampling water inside the small plastic beaker. Withdraw the moistened cotton ball and swab the entire measured area on the surface. Be careful not to lose too much water in the process. The cotton ball should be wet but not saturated or dripping. After swabbing the entire measured area, place the cotton ball back into the beaker and swirl it in water. Be careful not to touch the water or the cotton ball with your unprotected fingers, as they can contaminate the sample. Wring out most of the water from the cotton ball, then swab the same measured area a second time. Repeat this process a minimum of 4 times using a fresh cotton ball each time. Obtain a fresh cotton ball and dry the area. All of the cotton balls should be in the beaker. Stir the cotton balls in the beaker of water for 2 minutes. Then wring out all of the cotton balls against the inside wall of the beaker and measure the final volume by pouring the extract into the graduated cylinder. Obtain a control sample using the same volume of water and the same number of cotton balls, but do not swab any surfaces. Allow the cotton balls to remain covered in water for 3 minutes. Any detectable chloride in the control sample will be deducted from the sample collected from the surface. Once the sample has been extracted from the surface using the swabbing methodology, there is a selection of methods that can be used to analyze the extract. I'll be discussing 2 primary methods, including chloride ion test strips and ferrous ion test strips. Note that the sample can also be analyzed for conductivity using a conductivity meter, or it can be analyzed using chloride ion detection tubes. These latter 2 methods will be described later in this webinar when we're looking at alternative methods of extraction and analysis. We're now ready to test the sample collected from the surface for chloride and ferrous ions. We'll first analyze the solution for chloride using the chloride ion test strip. Remove a test strip from the bottle and place the bottom of the strip into the plastic beaker containing the sample. You'll only need a few drops of solution to activate the test strip. Allow the sample to saturate the center orange-colored wick or column of the test strip. This takes approximately 5 minutes. The test strip is completely saturated when the yellow indicator string at the top of the strip, which is indicated by the red arrow on the slide, darkens. This indicates that the test is done. Remove the test strip from the beaker and locate the peak of the white mark on the orange wick or column. Read the Quantab unit value corresponding to the white peak from the scale, which is imprinted on the orange column. Each division between the numbers is 0.2 Quantab unit. Convert this value to parts per million, or ppm, of chloride using the conversion chart on the side of the bottle. Record the ppm value and the batch number from the bottle, as the chart on the bottle can change as a new batch of strips is manufactured. Enter all of the data into a chart similar to the one shown on the slide, then calculate the surface chloride concentration. For example, if the reading from the test strip was 124 part per million and 22.5 milliliters of water was used in the extraction, the concentration of chloride in the water is 2,790 micrograms. To obtain this value, we simply multiplied part per million by the amount of water we used. By dividing that number, which is micrograms of chloride, by the area extracted, the surface concentration is revealed. In this case, 2,790 divided by 225 square centimeters results in a surface concentration of 12.4 micrograms per square centimeter. Since the area sampled was 10 times the quantity of water used in the extraction, the surface concentration is simply 1/10 of the concentration of chloride in the extract. However, any size area and any amount of water can be used as long as those are both recorded. If the specification requires you to measure the ferrous ion concentration, you can use the same sample that you used to test for chloride, just use a different indicator strip. Remove a ferrous ion indicator strip from the bottle and dip the lower end of the strip into the beaker of solution. Make sure at least 1/2 inch of the lower portion of the test strip is saturated. Remove the test strip from the beaker and shake off any excess liquid. Wait 10 seconds, then compare the color of the indicator strip to the color chart on the side of the test strip bottle. Record the value from the color chart. The values are in milligrams per liter, which is the same as parts per million. So we can use the same procedure to calculate the surface concentration of ferrous ion that we use to calculate for surface concentration of chloride. The value from the color chart is simply multiplied by the amount of water used in the extraction, then divided by the area sampled to obtain the surface concentration of soluble ferrous ion contamination. The Chlor Test kit employs the latex sleeve procedure to extract samples from the surface. The prepackaged kit contains the necessary equipment to extract samples from the surface, then analyze those samples for chloride contamination. Each kit contains 5 test packets. Each packet includes a latex sleeve, an extract solution bottle, and a chloride ion detection tube. A metal tube breaker, aspirator bulb, and instructions are also provided. The latex sleeve can be used in any position, conforms to rounded surfaces, and the solution is not subject to evaporation from hot surfaces. Remove the cap from the extract solution bottle and pour the entire contents into the latex sleeve. The extraction liquid shown in the left image is slightly acidic, which reportedly improves the extraction efficiency. Peel the white pressure-sensitive adhesive strip backing from the latex sleeve to expose the adhesive. Remove the air from the sleeve by squeezing it between your fingers and thumb. Be careful not to spill any of the solution while you are evacuating the air from the sleeve. Select a test area, then firmly affix the latex sleeve to the surface by attaching the adhesive end of the sleeve to the test surface. The latex sleeve can be attached to horizontal or vertical surfaces or even overhead. Press firmly around the perimeter of the contact area to ensure you have a good seal between the surface and the latex sleeve. With one hand, lift and hold the free end of the latex sleeve upright so that the extraction solution comes in contact with the test surface. Use your fingers on the other hand to massage the solution through this latex sleeve for at least 2 minutes. This helps to pull the contamination from the surface into the solution. After the extraction is complete, carefully remove the latex sleeve from the test surface. Make sure that the extraction solution returns to the bottom of the latex sleeve before you remove it from the surface. For overhead or vertical surfaces, gravity will put it there. But for horizontal surfaces, you'll need to slide your fingers along the outside of the latex sleeve and push all of the solution into the closed end of the sleeve before removing it from the surface. After removing the latex sleeve from the surface, place it through the hole in the kit box lid with the open end of the sleeve up. The sample will remain in the bottom of the latex sleeve. Once the sample has been extracted from the surface using the latex sleeve and extraction solution, there is a selection of methods that can be used to analyze the extract. The chloride ion test strip and ferrous ion test strips that were described earlier can also be used to analyze the solution in the latex sleeve. The most common methods of analysis when using the latex sleeve extraction method include chloride ion detection tubes. The manufacturer offers a prepackaged test kit for analyzing chloride, nitrate, and sulfate ion. I'll describe the proper use of the chloride ion detection tubes first, then I'll describe the use of the test kit for the other two anions. Remove the chloride ion detection tube from the kit, making sure you do not touch the ends with your fingers. Use the metal tube end snapper, break off both ends of the tube. The ends of the tube will be very sharp. Keep the tube ends away from your eyes and fingers. Place the prepared tube into the test sleeve with the arrow and smaller numbers on the tube at the bottom. The arrow indicates the direction that the solution will flow through the tube, for example, upwards. Allow the tube to remain in the solution for at least 90 seconds or until the solution has wicked all the way to the top of the tube using capillary action. The cotton filaments at the top of the tube will turn from white to amber when the sample has reached the top. If the sample does not begin to travel up the tube after 30 seconds or so, you may need to help it. Place the aspirator bulb over the top end of the tube while the lower end is still in the solution, then give the bulb one squeeze. The suction will help to bring the solution into the tube. Carefully remove the black aspirator bulb and allow the tube to continue to draw the sample upwards until the cotton fibers at the top of the tube turn color. After the cotton filaments turn from white to amber, remove the tube immediately from the latex sleeve and read the value on the glass tube at the interface of the pink-white color shift. The pink coloration of the silver dichromate inside the tube is normal, while the white coloration indicates the presence of chloride as silver chloride is generated. The value at the pink-white interface indicated by the red arrow on the slide is the amount of chloride present in the test solution. This value is expressed in parts per million, or ppm. The chloride detection tubes generally range from non-detectable to 60 parts per million chloride. If you are required to analyze an extracted solution for nitrate or sulfate contamination, a prepackaged test kit is available, which includes all of the extraction and analysis tools you will need, in addition to the chloride ion detection tubes I just described. The test kit includes 5 extraction kits, 5 chloride ion detection tubes, 5 nitrate ion test strips, 5 autovial filters and cone filters, 5 glass sample bottles, 5 sulfate reagent bottles, each containing 1/10 of a gram of barium chloride, and a color meter for sulfate detection. Replacement kits for all of the expendable items are available. Naturally, the color meter is multi-use. If the specification requires you to measure the nitrate ion concentration, you can use the same sample that you use to test for chloride. Again, just use a different indicator strip. Remove a test strip from the protective packaging and dip the lower end of the strip into the test sleeve containing the extracted solution for 2 seconds. Remove the strip, shake off the excess liquid, then compare the color of the indicator strip to the color chart provided with the test strips. Record the value from the color chart. The values on the chart are in parts per million. The value from the color chart is multiplied by the amount of water used in the extraction. Then that value is divided by the area sampled to obtain the surface concentration of soluble nitrate ion contamination. Unlike chloride, ferrous ion, and nitrate, which can be analyzed simply using test strips or detection tubes, the analysis of sulfate is more complex and requires the use of an instrument known as a colorimeter. Once the sample is collected from the surface, it is poured through a paper funnel into an auto vial and filtered through an auto vial filter into a glass vial. A minimum of 7 milliliters of solution is required for this analysis. After the extract is filtered, replace the cap on the glass vial and remove any fingerprints from the exterior of the vial using the cotton cloth provided with the kit. Any remaining fingerprints can affect the colorimeter measurement. Insert the glass vial containing the sample into the colorimeter. A white vertical index line on the side of the vial must be in line with the point of the triangle embossed on the meter housing. Close the lid of the meter and depress the 0 button until BLA is displayed on the meter. This blanks out any coloration. After zeroing the meter, remove the sample from the meter, open the glass vial, and add the entire contents of one of the bottles labeled 0.1 gram barium chloride. Cap the vial and shake it vigorously for 10 seconds, then wipe it to remove any fingerprints. Place the vial back into the meter, being sure to index it into position. Then close the lid and push the read button at this time. The meter will display the sulfate concentration in parts per million, or ppm. The opening of the latex sleeve was designed at 10 square centimeters. The amount of prepackaged extraction solution is 10 milliliters. Since the area tested and the volume of solution are both 10, they cancel one another out of the equation, so the reading in parts per million on the chloride ion detection tube is the surface concentration in micrograms per square centimeter. This is shown on the slide. There are 2 latex cells that can be used to collect a sample from the surface. They are both referred to as Bresley. The Bresley patch is shown in the upper image on the slide. It is an adhesive latex cell. The sampling area of the latex cell is 12.25 square centimeters and is square in shape. The Bresley sampler is also an adhesive latex cell. The sampling area of this latex cell is 12.5 square centimeters and is round. The procedure for collecting a sample from the surface using these 2 latex cells is essentially the same. The patch or cell is injected with an extraction solution or distilled water using a syringe. The solution is then withdrawn and tested for anions or conductivity. Like the latex sleeve, the latex patch or cell can be used in any position, conforms to rounded surfaces, and the solution, once injected, is not subject to evaporation from hot surfaces. Once a test area is selected, peel the label backing from the adhesive side of the latex cell and discard the label. This will expose the adhesive. Carefully press the center of the non-adhesive side of the patch with your fingers to punch out the foam to create a void area. This foam piece is also discarded. Attach the latex cell to the test surface, adhesive side down. Press firmly around the foam border of the latex cell to ensure a good seal. You have now created a sampling cell that will retain the extraction solution once it's placed inside. Using an empty 5 milliliter syringe, insert the needle through the top of the foam border, then continue to slide the syringe needle into the latex cell until it is just visible through the semi-translucent top. Withdraw the syringe plunger to evacuate the air from inside the cell. This will help prevent overpressurizing of the patch during the sample collection. You will note that a vacuum is created inside the cell because the top of the cell will be drawn in towards the test surface. Carefully remove the syringe needle from the cell by sliding the needle back through the foam border. Dispense the desired quantity of distilled water or extraction fluid into a clean plastic beaker or other small container. Draw the liquid into the syringe using the syringe needle. If you overfill the syringe, you can expel the excess by slowly depressing the syringe plunger until the desired quantity is achieved. Never expel liquid back into the source container, as you may cause it to become contaminated. You can use any amount of liquid, but 2.5 or 3 milliliters is common. Record the amount of extraction liquid used. The extraction liquid shown in the upper image is slightly acidic, which reportedly improves the extraction efficiency. A specific test method may require the use of this extraction liquid versus demineralized water. Carefully insert the syringe needle through the top of the foam border, then continue to slide the syringe needle into the void area of the cell until it is visible through the semi-translucent top. Slowly inject the liquid into the cell. Once all of the liquid is injected, carefully slide the needle back to the foam border, but do not remove the needle from the cell. Carefully rub and tap using moderate pressure the top of this cell for about 1 minute. This agitates the liquid inside the cell and helps extract the contaminants. Slide the needle back into the cell and evacuate the solution. Slowly inject the liquid back into the cell and agitate the surface again. Repeat this procedure at least 10 times. After the final time, evacuate as much of the liquid from the latex cell as possible using the syringe. Empty the contents of the syringe into a small plastic beaker or other plastic container for analysis. Note that the slide makes reference to massaging the inside of the patch or cell for 10 to 15 seconds and repeating that process 4 times, once plus 3. ISO recommends a 1-minute dwell time and 10 injections for a total of 10 minutes elapsed extraction time. Once the sample has been extracted from the surface using the patch or cell and the extraction solution, there is a selection of methods that can be used to analyze that extract. The chloride ion test strips and detection tubes that were described earlier can be used. Other methods commonly used include drop titration and conductivity meters. I'll review these procedures since they've not been described with other methods. A prepackaged kit containing 50 latex cells, extraction fluid, syringes, a clear vial for analysis of the extracted sample, titration chemicals, and instructions has been assembled by the manufacturer. Drop titration is a method of analysis where drops of specific types of chemical solutions are added to the extraction sample, and the sample is examined for color change. The number of drops required to change the color of the solution indicates the concentration of chloride in that solution. 3 bottles of chemical solutions called a titration set are included in the prepackaged kit. By adding drops of the chemical solutions in the correct sequence to the sample, the amount of chloride can be measured and recorded. To perform the drop titration method, add 2 drops from bottle 1 to the sample. Carefully swirl the sample to ensure the drops blend into the sample. Then add 2 drops from bottle 2 to the sample. Again, carefully swirl the sample to ensure the drops blend with the sample. The sample will turn from clear to yellow once these drops are added. Add 1 drop at a time from bottle 4 to the sample. Carefully swirl the beaker after each drop is added to ensure it blends with the sample. Count the number of drops required to turn the sample from yellow to blue. Note that bottle 3 supplied with an earlier version of the kit is no longer provided. The concentration of chloride in the solution is based on the number of drops added to the extracted solution to cause it to turn from yellow to blue. Since the size of the drop dispensed from the bottle is not accurately controlled, for example, like it would with an auto titrator, a range of surface chloride concentration is reported. This is shown in the chart. For example, if 3 drops from bottle 4 were required to create the change in color, then the surface concentration of chloride is reported as 4 to 6 micrograms per square centimeter. If the specific type of ion contamination is not of interest or is assumed, a conductivity meter can be used to measure the conductivity of the extracted sample. One type of conductivity meter that can accommodate a relatively small sample volume is shown in the slide. There are others of similar design. The accuracy of the conductivity meter should be verified before each use with the standard solution provided with the meter. After the accuracy verification is complete, the sensor should be thoroughly rinsed with distilled water. Next, place a few drops of the liquid used to perform the surface extraction onto the sensor. The meter will display the conductivity of the source water. This value is recorded as the conductivity of the blank and must be deducted from the conductivity of the extracted sample once it's tested. Remove the sample from the sensor. Place a few drops of the extracted sample onto the sensor. Record this value as the conductivity of the extract. Calculate the conductivity caused by salt contamination by subtracting the value of the conductivity of the blank from the conductivity of the extracted sample. Note that distilled water must be used for the extraction when a conductivity meter is used for analysis. The proprietary extraction liquids, which are generally slightly acidic, cannot be used with conductivity meters. Direct sampling eliminates possible contamination by obtaining extraction liquid directly from the bottle of distilled water supplied with the kit without transferring to a container, and by applying the extracted sample directly onto the measuring cell of the conductivity meter. A prepackaged direct sampling kit includes a digital conductivity meter that can accommodate a small sample volume, a buffer solution and rinse to verify accuracy of the conductivity meter, 25 latex patches, 6 plastic beakers, 500 milliliters of distilled water, and a single 20 milliliter syringe. The procedures used to perform the direct sampling procedure are similar to those already described for some of the other methods. The amount of the solution used in the extraction is slightly less. First, the accuracy of the conductivity meter should be verified before each use using the buffer solution provided with the kit. After the accuracy verification is complete, the sensor should be thoroughly rinsed with the rinsing solution that's also provided with the kit. Place a few drops of distilled water supplied with the kit onto the sensor of the conductivity meter. The meter will display the conductivity of the distilled water. This value is ultimately deducted from the conductivity of the extracted sample once it is tested. Remove the blank sample from the sensor. Obtain a sample from the surface using the latex batch or cell method previously described in this webinar. In this case, 2.5 milliliters of distilled water is injected into the cell once the air has been evacuated. Once the extraction procedure is complete, place a few drops of the extracted sample onto the sensor. Record this value as the conductivity of the extract. Calculate the conductivity caused by soluble salt contamination by subtracting the value of the conductivity of the blank from the conductivity of the extracted value. One of the newer methods to come into the marketplace is the SaltSmart, which is a saturated contact pad developed by the National Surface Treatment Center, or NSTC. The pad uses precision fluid flow to extract soluble salt contamination from the surface. Once the extraction is completed, the strip containing the contact pad is connected to a conductivity meter to determine the soluble salt concentration. A prepackaged kit contains a specially designed conductivity meter, test strips, distilled water ampules, and instructions. The user must supply painter's tape to secure the test strip to the surface. The test strips and water ampules are all disposable. To use the SaltSmart extraction and analysis procedure, first remove the test strip from the sealed package as shown in image 2 on the slide, taking care not to touch the sensor as depicted in image 3. Squeeze the neck of the water ampule containing the pre-measured distilled water as illustrated on image 4 in the slide. This breaks the seal and opens the ampule along with water flow into the test strip. Fully connect the water ampule onto the test strip as shown in Figure 5 on the slide. Make sure the ampule is completely connected to the test strip as demonstrated by the check mark Figure 5. An incorrect connection of the ampule to the test strip is noted in Figure 5 by the X. Noted in Figure 6 as noted in Figure 5 as the X. Position the test strip at a 10-degree angle as illustrated in Figure 7 on the slide so that the water from the ampule flows into the test strip. Use a strip of painter's tape or other suitable non-residue tape to hold the sensor onto the surface while under test, as illustrated in Figure 8. If performing the test overhead, use a second piece of tape to secure the water ampule, as shown in Figure 9 on the slide. After approximately 8 to 10 minutes, remove the test strip from the surface and connect the test strip directly to the conductivity meter, as shown in Figure 10, and read the conductivity value from the display. The meter will store the value and will date and time stamp each value. Up to 255 values can be stored, then uploaded to a computer using a USB connection. Dispose of the test strip and water ampule once the test is complete. These are not reusable. The soluble salt meter is a handheld automated method for extracting and detecting soluble salts on flat surfaces. Newly designed instrument heads allow for measurement on curved surfaces. Since the meter is attached to the surface using magnets, as indicated by the number 6 on the slide, its use is limited to carbon steel surfaces. The measurement area is circular and is fixed at 1,250 square millimeters. The prepackaged kit consists of a soluble salt meter with a rechargeable battery, a 500 milliliter bottle of distilled water that accommodates a fixed volume fluid dispenser, a 250 milliliter bottle of standard solution and syringe for verifying the accuracy of the meter, an AC adapter, a USB connection cable, data management software, and instructions. Prior to conducting an extraction and analysis of the surface, verify the accuracy of the conductivity meter by injecting the meter with the recommended quantity of calibration solution. Verify that the instrument display matches the conductivity of the standard solution, which is 84 microsiemens per centimeter. Thoroughly flush the meter using distilled water. To perform an extraction, attach the flexible hose from the deionized water fluid dispenser to the meter, then attach the meter to the surface. Inject 3 milliliters of deionized water into the measurement chamber with one press of the dispenser. The meter will agitate the solution and automatically obtain a reading, which is displayed on the LCD screen and simultaneously stored in memory. Once the reading is obtained, detach the meter and wipe the remaining water from the surface. Thoroughly flush the meter using water from the dose bottle so that it is ready for subsequent measurements. The stored values can be uploaded to the data management software using the USB cable. The Surface Salinity meter, which is manufactured in Japan, is similar to the soluble salt meter I just described, which is manufactured in the US. The surface salinity meter consists of a magnetic measurement cell connected to a conductivity meter. The lower image on the slide illustrates the contact surface of the magnetic cell, which consists of a series of 8 magnets and an automated stir bar in the center. An extraction and analysis of a carbon steel surface is performed by attaching the measurement cell to the surface and to the conductivity meter. The syringe supplied with the surface salinity meter is filled with 10 milliliters of distilled water supplied with the instrument. Immediately after injecting the water into the cell, the meter is powered up and the solution stir bar is activated. The clock on the display of the meter will switch to a countdown timer. Once the measurement is displayed on the meter, the stir bar can be stopped using the on-off switch on the top of the cell. The data is automatically stored by the meter. The cell must be rinsed with pure water prior to obtaining additional measurements from other test sites. The final method of extraction and analysis of soluble salt contamination described in this webinar is the concentric ring conductivity meter. A prepackaged kit contains 100 filter paper samples, gloves and tweezers, a 250 milliliter container of distilled water, dispensing syringes, and a conductivity meter. The extraction is performed using saturated filter paper, and the analysis is conducted using a concentric ring conductivity meter. To extract a sample from the surface, a piece of filter paper is saturated with 1.6 milliliters of distilled water using the dispensing syringe. Saturate the paper and place it in contact with the surface using the plastic tweezers. The concentric ring conductivity meter contains a timer that is activated by pressing one of the buttons on the meter. This helps to ensure an adequate contact time between the saturated paper and the test surface. Once the timer sounds, the filter paper is removed from the surface using the tweezers and is placed on the center area of the conductivity meter. Once the filter paper is in place and the lid of the meter is closed, the meter is again activated using one of the buttons, and the value is displayed on the meter. The meter converts the conductivity to surface concentration, revealing the value in micrograms per square centimeter. Appendix B1 in SSPC Guide 15 provides a formula to convert a conductivity value generated using a conductivity meter over to surface concentration. The formula is E1 is equal to 0.5 times S times V over A, where E1 is the surface concentration of chloride in micrograms per square centimeter, for example, what we are solving for. S is the conductivity in microsiemens per centimeter. V is the volume of water used to collect a sample from the surface in milliliters. And A is the area of the sample collection in square centimeters. For example, if the conductivity is measured at 70 microsiemens per centimeter, the volume of extraction liquid used was 2 milliliters, and the area extracted was 12.25 square centimeters, the estimated surface concentration of sodium chloride is 5.6 micrograms per square centimeter. So in summary, we have described the purpose of SSPC's Guide 15. We've listed 6 parts to the ISO standard addressing soluble salt extraction and analysis procedures. We've described the difference between sample extraction and sample analysis. We've described 6 different methods for extraction of a sample and 7 different methods for analysis of the extracted samples. We've also learned how to calculate surface concentrations based on the concentration of soluble salt in the collected sample, the sample volume, and the size of the area where the extraction occurred. And we learned how to convert conductivity to the equivalent surface concentration. Thank you for listening to this webinar on methods for the detection of soluble salts. To enjoy viewing other videos and webinars like this one, visit the Digital Learning Series tab on KTAUniversity.com.